So first of all, bonjour à tous. D'abord, un petit annonce technique. Please welcome everybody. We would like you to switch off your microphone for the time being, maybe until there is time for questions. Or if you have a question during the talk, don't hesitate to unmute yourself and ask. I want to welcome everybody again to the 8th edition of the CRM Nuremberg lectures on geometric analysis. They are named after Louis Nuremberg, who lived in Montreal in his youth and has been an undergraduate student at McGill. But primarily the lecture's name honors the great achievements of Nuremberg as mathematicians. And we had the pleasure of having Louis Nuremberg in the audience in the first editions of the lectures. And in fact, it was at the end of the second year, 2015, when Louis Nuremberg was informed that he was awarded the Abel Prize. So it was quite a pleasant and historic moment. The CRM series of lectures named after him continues to honor great current achievements in geometric analysis, and our impressive list of speakers is a living proof. In this spirit, this year we have the pleasure to have Bo'az Klartag and Yuan-Si Chen, who will deliver these special talks. Today, for the first lecture, we are happy to have Professor Klartag from Weizmann Institute of Science, former ICM speaker and winner of 2008 European Math Society Prize and 2010 Erdös Prize. Professor Klartag is particularly known for fundamental contributions to high-dimensional and asymptotic geometric analysis. I'm pleased to give him the floor to talk about this field because this is in particular very close to my heart. So the title of the first lecture is Convexity and High-Dimensional Phenomena. So please.
Thank you, Alina, also for this generous introduction, for inviting me to speak here at this lecture. It is a honor for me to give these lectures now in memory of a great mathematician such as Louis Nuremberg. The subject of my lecture is the interplay between two mathematical subjects. The first is convexity, which is the geometric study of say convex bodies, classically and related objects. And the second is high-dimensional phenomena, which is the study of mathematical problems and systems of high dimension of many parameters. And I'm going to begin with an introduction to a certain point of view on high-dimensional phenomena. Okay, so the questions that we're going to ask is whether there exist some general, non-trivial principles in high-dimensional geometry or in the study of high-dimensional systems or problems. And I think that historically, one of the first examples arise from the study of probability measures in high dimension, and this is through the classical central limit theorem. So let me tell you or remind you about the CLT. So the central limit theorem is concerned with a collection of independent random variables, x1, x2, up to xn, and we would like to group them in a random vector in Rn, which we denote by x. Okay, and we assume that n is very large because we care about high dimensions. And then, as it turns out, under some mild regularity assumptions, you can find there exist coefficients theta 1, theta 2, up to theta n, such that this linear combination, this weighted combination of sum of theta times xi is approximately a Gaussian random variable. And in fact, if you properly normalize it, so it's more common to normalize these random variables and say make all of them of average 0 and variance 1. And in this case, this vector of coefficients could be taken to be just all ones vector, I mean, 1 divided by square root of n. And maybe this is the familiar form of the classical central limit theorem. The sum of x over root of n is approximately Gaussian, where x are independent random variables of mean 0, variance 1, and maybe some mild extra conditions, so maybe uniform bound on third mode or something like that. But also, actually, it's not only this unit vectors that works. And under this normalization of mean 0, variance 1, we also know that most choices of vectors of coefficients, theta 1 up to theta n, most choices of unit vectors of coefficient work. And by most, I refer to the uniform probability measure on the sphere. So it makes sense to take vector coefficients on the unit sphere, sum of spheres plus 1, because this way you get random variable of variance 1. And if you look at the inverse condition on various in bound or something of this sort, you would see that for a typical choice of vector of coefficients, if you look at the scalar product of x with theta, this sum of theta times xi, you'd get approximately a Gaussian distribution. There is another way to look at a more maybe geometric point of view on this central limit theorem. And this, so let's look at the case, for example, where these random variables are uniform in the interval. So x1, x2 are just uniform in the interval, say, -1, 1. In this case, the random vector x is uniform in a cube in high dimension, the product density. And what is the meaning of looking at sum of theta xi? What is the meaning of looking at x times theta? The meaning is that we project x to the direction of theta. Okay, so if I let me try to draw, if I draw this cube, I mean it's only two-dimensional, and this is the direction of theta, then I look at the projection of x in the direction of theta, and the conclusion of the central limit theorem is that if I scan the volume of parallel hyperplanes orthogonal to theta, then they obey kind of the Gaussian law, and this is true for many different directions. Okay, so this is the central limit theorem is a regularity property in high dimensions. It shows that if you have a product measure in high dimension, measure that is composed of independent random variables, then these measures have some regularity properties. So they have marginals that are approximately Gaussian. In the same formula, e to minus t squared over 2 over root of 2 pi, the same formula appears no matter what are the precise details of the independent random variables that constitute of this product measure, that constitute of this product measure. Okay, so product measures, you could say, are maybe one of the main examples for measures in high dimension with a very clear structure that are composed of basically building blocks. But of course, there's also other examples. You could have, I don't know, Markov chain, you could have approximately independent random variables, and also in these cases, you get central limit theorem. Now, another thing that could help you to analyze and to show some regularity of high dimensional probability distributions is symmetries. So if you have a distribution which is very symmetric, then it might be easier to analyze. For instance, if you study the uniform probability distribution on the sphere, on the high dimensional sphere, which is a very symmetric distribution, it is a classical fact that uniform measure on the sphere in high dimensions also have marginals that approximately Gaussian. This was known, I think, in the 19th century. So structure and symmetry are properties of a distribution that help you analyze it and help you show some regularity. And what we will try to show, to argue in this lecture is that in some cases you can replace structure and symmetry by convexity. And we should see that convexity condition fit rather well with high dimensionality. Now, what do I mean by convexity conditions? So for now, let's consider two cases. So the first case of probability measured in high dimension with convexity property is just a uniform measure on a convex domain Rn. So you put some, I don't know, take some polytope and take the convex set, you get some compact convex set and look at the uniform measures there. And more generally, you can consider log concave measures. So log concave measures, okay, these are defined as follows. So these are supported on some convex set, but the density is not uniform, but it is e to minus h with some convex function h. And we'll discuss them here later. The Gaussian is an example for this thing. It is a slight generalization of uniform measure on convex domains. Okay, and we hope to show you that for large dimension n, you would see that the geometry of R enforces some regularity, and it's with the help of convexity, you can harness this to formulate some non-trivial. Okay, or this is at least the big plan. So these are rather general words. I guess it's better to look at some example. So I want to analyze in quite a detail an example. And this is the case of the convex value, which is the Euclidean ball in n dimensions. And in fact, most of the mass of the ball is close to its boundary. So I'll just discuss the sphere. It's small as this. Everything I'm going to say applies probably also for the Euclidean ball. But the sphere is a homogeneous space. All points are the same. It's slightly nicer to formulate theorems. Okay, so we have the sphere, Sn minus 1. And by the way, as Alina said, I mean, please feel free to stop it at any point and ask questions or make comments. I'll be happy. It's completely fine. Don't have to wait till the end. Okay, so we have this sphere. This is the Euclidean norm, points of distance 1 from the origin of the sphere. And we write sigma for the uniform measure of the sphere normalized to be a probability measure. This is sigma n minus 1. Okay, and we are interested in epsilon neighborhoods of sets. So given a set A on the sphere and some parameter epsilon, we'll consider the set A epsilon, which is the set of all points in the sphere whose distance from A is at most epsilon. So for instance, let's look at the hemisphere. The hemisphere is the set of all points whose first coordinates here it's negative. This is the southern hemisphere. And this is a set of measure 1/2 because sigma is a probability measure and clearly the hemisphere is half of the sphere. And now what is the epsilon neighborhood of the hemisphere? Well, it consists of the hemisphere itself plus some little color, some little strip about the equator of which epsilon. Okay, so this is the epsilon neighborhood of the hemisphere. And now, what is the measure of the epsilon of the hemisphere? So the hemisphere itself is 1/2, but if you take the epsilon of the hemisphere, you could formulate it in a probabilistic language. You could say that this is the probability of y1 to be smaller than epsilon. Actually, sin epsilon because I took the geodesic distance. Don't pay too much attention. So y1 smaller than epsilon, where y is just a random vector uniform distributed over the high-dimensional sphere. Okay. Now we know, I'll discuss it later, even I may explain it maybe later. We know that if you look at the uniform distribution of the sphere, we know that the marginal, say y1, is approximately a Gaussian random variable. Okay, and moreover, it has expectation 0 because it's a centered sphere, and the y is going to be 1/n. Why is the variance of y1 1/n? Because y1 square has expectation 1/n, because y1 square plus y2 square up to yn square is some 1. So each of them is expectation 1/n. Okay, so y1 is square is 1/n. So y1 is roughly Gaussian of mean 0 and standard deviation 1/√n. Okay, and therefore we have this approximation of the measure of the epsilon of the hemisphere is roughly the probability of a Gaussian, of a standard Gaussian to be at most epsilon times √n, right? You have this √n factor because gamma over √n is approximately the first coordinate of y, the random vector on the sphere. Okay, good. Now, let's think of epsilon of being some small number but fixed. Maybe epsilon is 1/10. Okay, but n is going to infinity. And therefore, this probability here, the probability of Gaussian to be smaller than epsilon √n, is very close to 1. I mean, it's a probability of a Gaussian to be at most √n standard deviation time 1/10 above its mean. And this is roughly, the complementary probability is exponentially smaller dimension n. So what you conclude is that the amount of mass of this hemisphere plus this little strip about the equator is almost 1. It's 1 minus e to minus the dimension. And of course, this is also true for the northern hemisphere. So what we conclude is that lots of mass is located very close to the equator. When you just take this tiny neighbor, it looks tiny in dimension 3, it actually captures large parts of the sphere. Okay, so let me say it again. So the amount of volume of the high-dimensional sphere whose distance from the equator is more than 1/10. So anything outside this little strip is tiny. The amount of mass is just e to minus n of the total volume of the sphere. And there are some universal constants. I don't know, half, this is half, and this could be 2 floating around. Okay, so what of the mass of the sphere in high dimension is considered an very narrow strip near the equator, but this is also true for any equator, right? The sphere is symmetric space. There are so many equators. So this is some of the startling effects that the mass is close to the equator, but this is true for all equators. And this effect is sometimes called the constellation of measured phenomena. And I learned from Vital Milman that a nice way to depict the high-dimensional sphere is not like a three-dimensional circle like this, but maybe it's better to draw it like this shape here to demonstrate the fact that the mass is kind of near the equator, not so much mass far away from the equator. Of course, this is not symmetric, but I mean, that's what you can do into the image. Okay, now this is only about the hemisphere, and the way to use it analytically is one way is to do it through the isoperimetric inequality that goes back to Paul Levin and to Schmidt. So what is the asymptomatic problem? So this is the following question. You look on all, say, barrel sets, measurable sets A on the sphere of measure 1/2, and you have some fixed number epsilon. And among all of these sets, you want to look for the set that has minimal volume of epsilon enlargement. Okay, so you have some, this is the sphere, you have some, let me do it. You have some set A whose measure is 1/2, and you want to minimize the little corners that you get, the little strip by the equator. It's not totally a big surprise that that the answer is known, that it is actually a hemisphere. Right? Among all sets of measure 1/2 on the sphere, clearly the hemisphere stands out. And this is indeed true, this is one inequality. So we know that for any set of measure 1/2 on the sphere, the measure of its epsilon enlargement is at least what you get for the hemisphere. But we just said that from the hemisphere, you get something very close to 1. So you conclude that whenever you have a set A or whose measure is 1/2, its epsilon enlargement is at least 1 minus something which is tiny. It's really, really close to 1. Its epsilon neighborhood, the epsilon neighborhood of any subset of measure 1/2 on the sphere, covers basically the entire sphere, almost the entire sphere in sense of measure. Okay, and there is okay one immediate corollary, which is one of the many ways to use concentration of measure phenomena in analytic problems, and this corollary is about Lipschitz functions. So let's consider the case where you're given some function on the sphere, which is one Lipschitz. So f of x minus f of y is the most distance between x and y. So f varies in a reasonable manner. Okay, if you take some, I don't know, the function x1 squared plus x2 times x3 and divide by factor 10, then you're should get some one Lipschitz function. And let's write E for the average of f over the sphere. Then the claim is that the function f deviates very little from its average, from its mean. For any positive number epsilon, the amount of points, the measure of the set of points where every f deviates from its mean by more than epsilon is very small, is e2 minus epsilon squared times n. And this factor n here means that as the dimension increases, this goes to 0 very, very, very fast. Why is this true? Why is it true that deviates so little from the average? Let's try to explain the proof roughly. So let me try to do, so this is maybe the sphere, and let's look at the median. M will be the median of the function f, okay? So the median is, and let's look at the level set where f equals the median. Okay, so this is this level set. So EF is smaller than the median, EF is larger than the median, and so both sets are usually of set of measure 1/2. And therefore, the allowance is huge. So you understand that if you take a small neighborhood about the median, it has a very large measure. The measure is at least 1 minus the quantity which is written here. However, since f is 1 Lipschitz, you know that it's very close to m on this neighborhood of the median, right? Because it cannot be more than m plus epsilon, distance epsilon. And therefore you get that, well, most of the points on the sphere are such that the value of f at this point is very close to the median. And well, and you replace the median by the expectation, it's not so difficult. Okay, so this is one simple way, very simple way to harness this concentration measure in order to have some analytic property. So we understand that Lipschitz functions on a dimensional sphere, even though a priori you could think that they could vary, the values could be ranged from, I don't know, -1 to +1 or something of this sort. Well, in some ways they behave as if they were effectively constant, because if you sample 10 random points on the sphere, independent points on the sphere, and you evaluate your function f at these 10 points, then typically you obtain 10 numbers that are very close to one another. So the function behaves as if it really fits a bit. Okay, so let's get back to this classical observation, the fact that in high dimensions, if you take the margin of the sphere, you get approximately a Gaussian. What other distributions in high dimension have this property? They have this approximately Gaussian margin. In order to answer this question, it's a bit convenient, not necessarily, but it's a bit convenient to introduce some normalizations. We also add in the classical superlimit theory. So let us say that if you have a random vector x, it is normalized or isotropic. Actually, going to use the word isotropic all the time, or balanced, if the following conditions hold. So first of all, I require that it is centered. So we translate it so that the average, the expectation of xi should be 0 for all I. And second, we want to apply some linear transformation so that the covariance matrix of X would be the identity matrix. Okay, and it is always possible if you have any random vector X in Rn, which is a finite second moment and is not supporting hyperplane, you could always find a fine transformation. You can also always move it and stretch it linearly in some direction, orthogonal direction, and get this normalization condition. And the nice thing about this condition is that it guarantees that all one-dimensional marginals have mean 0 and variance 1. Okay, so you would aim to get a standard Gaussian distribution after you take the margin. Now comes an interesting observation, first explicitly written in Jacobs and Friedman in 1984, which finds some geometric condition that apparently has some relation to this probabilistic property of having approximately Gaussian marginals. So apparently, in order to have for some distribution, not independent random variables, just some distribution in high dimension, which is normalized as drop, in order to have approximately Gaussian marginals, it seems that you need most of the mass of the random vector X to be contained in a thin spherical shell. Okay, so there are these two concentric spheres, and the ratio of the radii is very close to 1. The spheres are, so what the region between them is pretty much a thin shell. And the condition is that the probability of X to belong to this shell should be very close to 1 somehow. And this geometric condition is somehow related to approximately Gaussian margins. Strange, but let us formulate it more precisely. So this is the Differential theorem that, so actually the Anchorage-Friedman's result was related to an earlier work by Sudakov. The proof by Sudakov was also generalized later by many authors. And let me formulate one version of this theorem. So this is, again, we have some random vector X in R, it's normalized. And suppose that there is some radius R. Actually, R would have to be root of n by our normalization. So we can actually assume R equals to root of n. Anyway, but suppose that there is radius R, and you know that if you divide the Euclidean norm of X by R, then this is very close to 1. The probability is that the Euclidean norm of X over R will deviate from 1 by more than epsilon is more than epsilon. That's the condition. So 1 minus epsilon of the mass is located in this thin spherical shell. That's the main assumption of this theorem. Then the conclusion is that you can find certain subset of directions. Let's call them the good directions. This is a rather large subset. It has a measure which is at least 1 minus e to minus root of n. And for any good direction theta, the random variable x times theta is small Kolmogorov distance to the standard Gaussian. The Kolmogorov distance is at most universal constant times epsilon plus 1 over n to some power. Okay, and by the way, this lecture, whenever I say these letters, capital C, small c, I just mean universal constant, just numerical constant. And whose value is actually known. I mean, you can give it's effective always for the case, so give you explicit numbers for this constant. Okay, so this is the Differential theorem by Sudakov and Jacobs and Friedman. It is known that this Differential theorem is something also necessary. I'll show it as an example soon. And let's just relate it to the classical central limit theorem. Let's verify that indeed, if you have independent identical distribution random variables, you have these product measures, let's say bounded force moments, then indeed it is satisfied. So we want to show that the Euclidean norm of X is very close to root of n, or equivalently that X squared over n is very close to 1. This expectation of x over n minus 1 squared, this is just the variance of x over n. And x squared is just the sum of x1 squared plus x2 squared up to xn squared. And variance is additive in independent random variables. So what you get is the variance of x1 squared, let's say, times n over n squared. So at the end, you get something which is like 1 over n. So typically for product measures, most of the mass is indeed located in a sphere whose width is small, it's just 1 over root n times the radius. Okay, let me just say roughly why is this theorem correct? Why would you connect Gaussian marginals to this shell theorem. This is supposed to be a shell. This thing. Okay. So why is it true? Well, the concentration of measured phenomena is one of the main ideas in the proof. How would you go about proving that? We fix some real number t, and let's define ft of theta to be the probability that x times theta is at most t. So we fix t and view this as a function of the sphere. Okay, theta varies, and we look this as a function of theta. And our goal is to prove that for most unit vectors theta and for all t, so typically this function ft of theta is roughly the probability that the Gaussian, standard Gaussian, will be smaller or equal than t. So we want to show two things. We want to show that ft of theta is roughly independent of theta, the same value for any theta. So ft should be effectively constant. And we want to show that this constant is roughly what you get for the Gaussian. And these two statements are more or less the two steps of the proof. So how would you show that ft is roughly constant, effectively constant? Well, you show that it deviates very little from its mean because it has good Lipschitz approximations. This is roughly the idea. And for this, you don't completely use the thin shell assumption because it works in greater generality. You use the thin shell assumption for the second step. So you want to know what is this number such that f is typically constant? What is this constant that f typically attains? What is the typical values of the function f? So for this, you need to compute the expectation, the integral of f over the sphere, right? The average of f over the sphere is its typical value. And since you need to average the function f over the sphere, you basically work, it's basically equivalent to taking your distribution and apply some spherical symmetrization to it and work with something which is spherically symmetric. And since most of the mass is close to a sphere, then you basically work with a small with an approximation to the uniform distribution of the sphere. Okay, so the average of the function f is more or less what you get for the sphere, or the root of n. And for the sphere, we know that you're going to get the Gaussian, what you get for the Gaussian. Okay, at least this is the rough idea for the proof of this differential theorem that goes back to Zokov in the 70s. Any questions or anything? Okay, so let me continue. Of course, not all distributions in high dimension have approximately Gaussian marginals. There are many cases where this thin shell condition is violated and you don't have Gaussian marginals. The simplest case is if you take a measure in high dimension that is supported on two spheres. You draw one sphere of radius R1, another sphere of radius R2, and you put half of the mass here, half of the mass there. Well, this does not have most of the mass close to a single sphere, right? This is two spheres, so there's no thin shell condition here. And indeed, if you take the uniform distributions on these two spheres, the marginals are going to be roughly a Gaussian mixture, going to be a mixture of two Gaussians of different variants, which is quite far from a Gaussian. So this is one way to validate the thin shell condition. And as you could see, the main problem in this example, the main problem in the sense that you don't see these Gaussian marginals, is you kind of have a mixture of two distributions that have not so much to do with each other. You have this mixture of different scales. And some 20 years ago, there was a suggestion, conjecture by Antila Bolen-Pirisinaki and by Bremen-Fucht, that perhaps a good way to rule out such examples is to make some convexity conditions. So maybe you could say that convex bodies in high dimension are kind of inherently of a single scale, that you cannot have this example of two spheres of very different radii that each of them captures large part of the convex set. So somehow, at least very heuristically, you might want to say that, okay, suppose you have, I don't know, some region of the convex set which whose scale is something like 10 times 1, you have another region where the scale is something like 1 times 10, then the convex body is to contain the convex hull of these two things. So it cannot, there should be some interaction at least between the two components. So this is the very rough heuristic. I don't know if it's very convincing. So let's discuss some more mathematical properties of convex sets. So what's special about convex sets? Why would you study these convex sets in high dimension? One of the first things to know about convex sets is the classical Boole-Minkowski inequality from 1887 by Boole. I mean, Minkowski added the equality case later. And it is concerned with this sum-set operation, or if you want this midpoint operation of A plus B over 2. So given two measurable sets, A and B should be Bo'az sets for some reason, and you look on the following set. So you take all pairs of points, A from A and B from B, and you look at A plus B over 2, just the midpoint of these 2 points. The collection of all midpoints, apparently, is not so small measure. So always the volume of A plus B over 2 is at least the geometric average of the volume of A and the volume of B. And volume is just a big measure in Rn. Okay, so this is the Minkowski inequality. And actually, even though convex sets are not mentioned in its formulation, it says quite a lot about convex sets. In the equality case, we have convexity conditions. The equality is more or less requires that A and B will be convex up to measure 0 or something like this. The Minkowski inequality in particular, it tells you that marginals of uniform distribution convex bodies are log concave. So let me say it again. If you have a density function, probability density in Rn, which is supporting a convex set, and it equals E2 minus h for convex function h, then we call this density function log concave. Okay, so they look kind of like, so a convex function, so h is a convex is something like this, so log concave is something like this shape here. E2 minus, say, x squared is an example for log concave. This is the Gaussian density, is log concave. And also you could take the characteristic function of a convex set, right? Just the constant function of this convex set is perfectly fine log concave measure. And actually, when you pass from this class of convex sets to the class of log concave densities, you get a slightly larger class, but it's now closed under many operations. Because, for example, log concave probability measures are closed under the operation of convolution. They're closed under the operation of a marginal. If you take any marginal of any dimension of some log concave measure, you get again something which is log concave. Okay, so it is somewhat more convenient to work with log concave measures than to work with uniform measures on convex bodies, even though the theorems could be formulated only for convex bodies. Okay, so let me just mention 2 more consequences of the Minkowski inequality, which I like. So, and they are also usually proved using this point of view of passing to log concave measures. So the first theorem is due to Hensley from 1980 in the central symmetric case and to Frederici in the general case in 1999. You consider a convex body in Rn, just compact convex sets, your favorite polytope, you normalize it. So asymptotic normalization, Barrett center at the origin and combines matrix identity. Then, as it turns out, if you slice it with a hyperplane, okay, then you kind of know that the volume, the minus 1 dimensional volume of this slice, this is say H1, this is H2, take just 2 hyperplanes to origin, does not depend that much on H1 or on the hyperplane in which you intersect the convex set. So for any 2 H1 and H2, the ratio of the minus 1 dimensional volume of the intersection of K with H1 and with H2 is bounded. You can never get more than universal constant. I actually wrote this constant square root of 6 here. So this is quite a remarkable fact about convex bodies in high dimension. It's also true for log concave measures. And this is proven by projecting to 1 dimension and observing that after projecting to 1 dimension, you get some log concave distribution, and you know its variance is 1 by the asymptotic normalization, and the variance, if the variance is 1, then its maximal density, the density of the origin is also turned out to be close to 1, and therefore the volume of this section is roughly known to you and does not depend so much on the direction. Another example for consequence of Minkowski inequality is the reverse order inequality. So for linear functionals, actually it's also true for polynomials of degree 2 or 3 or more. You can reverse the Erdös inequality. The LQ norm is larger than the LP norm if you're larger than P, but not by much, by some in a bounded way. Okay, so this is a property that correct for any margin of a convex set, any log concave distribution. What can you say? Can you say more about a typical direction? Do you have something like the central limit theorem? So the answer is yes, and yes, we do have a central limit theorem for convex sets. So let me read out the formulation of this theorem. So suppose that you have a random vector x in Rn as a topic normalization and a a uniform monoconvex set or some low concave density. Then we have a collection of good directions. This collection of good direction is pretty large. It has density, it has measured at least 1 minus e to minus root of n. And for any such good direction theta, we know that the margin of x in direction theta, the scalar product of x times theta, is close in total variation to the Gaussian density. The difference, the distance in the total variation metric is at most c over n to the alpha, where this c and alpha are universal constants. Okay, so in addition to the case of independent random variables and weakly dependent and the case of systematic distributions, we also have some such regularity for low concave distributions. We have this universality property that you always get the same approximation by the Gaussian. Okay, let me again tell you quickly why is this theorem correct. So as we said, we need to prove a thin shell bound. We need to explain why most of the mass is in thin spherical shell. Or in other words, we need to explain why convexity tells you that convexity in anisotropicity tells you that the Euclidean of x over root of n is typically close to 1, that the difference of x squared over n minus 1 is very small, the correct expectation is the most constant over n to the alpha. Okay, this is what we need to prove. By the way, so okay, if you're normalized, most of the mass is close to a sphere. If you don't assume any normalization, then you could say that most of the mass of your convex body is close to the surface of an ellipsoid, right? Because normalization is just a linear map, so there's always an ellipsoid that captures 99%. That whose boundary there is a tiny neighborhood of its boundaries that captures most of the mass of your convex body. Okay, so how would you prove the thin shell property of convex bodies? So the idea is again to use this constante of measure phenomena, and you do some tricks. You kind of project to some lower dimensional subspace, and you show that variance functions are roughly on the sphere roughly constant, and this means that somehow you get some distribution which is approximately radial in the lower dimension, because if function of the sphere is roughly constant, it means that density is roughly radial in high dimensions in some cases. And then you would use smarters in some way to the approximately radial case. And then you just need to prove a lemma about distributions that are both low concave, well, not both, but low concave, isotropic, and radial. And for these things, these are just kind of one-dimensional problems. If it's radial, you manage to prove directly that indeed most of the mass is in a thin spherical shell. Okay, let me just tell you quickly about some variants of this of the central limit theorem for convex sets. So first of all, there is a multidimensional version proven jointly with Ronald done in 2008. So again, we have a random vector x in Rn with a low concave density. You could make it uniform in a convex set. You have some dimension L, which is most n to power alpha, where alpha is some, I don't know, 1 over 50, some universal constant. Then the conclusion is that you could find a collection of L-dimensional subspaces. So this is the Grassmannian of L-dimensional space of Rn. This calligraphic E is the collection of good subspaces with respect to X. And the measure of this set of subspaces is pretty large. The Grassmannian has this Hall probability measure. So this is the way we measure collections from the Grassmannian. You know that this most subspace of the Grassmannian are good subspaces. And for any such good subspace E, we may assert two things. So first of all, the L1 distance, total variation distance between the projection of X onto E and the standard Gaussian distribution in E is very small. It decays C over n to the alpha, so some universal constant alpha. So we are close to the Gaussian in total variation sense. And moreover, in large parts of E, we can even bound the ratio of the density of the projection of X onto E and the standard Gaussian density. This is very close to 1 in large part of the subspace E. Okay, so in various senses, you are close to Gaussian and up to the dimension, which is some small power of n. one more theorem or a corollary is about convexity without the topic normalization, but you don't always have it, of course. So let's now suppose that X is some random vector in Rn, which is distributed uniformly in some arbitrary convex body, no restriction whatsoever. So you can even take things which look, I don't know, like almost one-dimensional thing. You could consider a distribution which is, it should be a body, it should have non-empty interior, it should be compact. But other than that, it could be anything else. So you could take something which is roughly a segment. So it's a very elongated cylinder, okay? And the extra dimensions are really tiny. If your distribution of this sort, then of course a typical marginal is not at all a Gaussian. A typical marginal will barely see the many dimensions, will just be almost uniform on an interval, right? I mean, you basically do for the on an interval. However, even in this particular case, you could find some marginals. You could find a projection which annihilates this big direction and make the distribution roughly Gaussian in total variation sense. So to be Gaussian with very tiny variance, so theta would not be unit vector if you want to get the standard Gaussian. But you can always find at least one vector, not unit vector, so that the margin of X in this direction is approximately standard Gaussian. Okay, good. But of course, if your distribution is normalized, I don't know, like say the uniformation on the cube or things like that, then you know that most marginals are approximately Gaussian. And the very few direction in which you observe, say, uniform distribution are very rare. If you project in the direction of 1, 0, 0, 0, you get roughly uniform, but this is very rare. In general, you get many approximate Gaussian margins. Okay, so let's compare this central limit theorem for convexity with Bo'az's theorem. Bo'az's theorem is an earlier manifestation of this concentration of measurable phenomena, and this is about the geometric projection of a set. You just take all points on K, you project them to E, and you get the projection of K onto the Seidel space E. And Millman's form for Bo'az's theorem tells you that if you have a convex body and a parameter epsilon, then you can find projections, geometric projection of this convex body, which are approximately Euclidean body. So if you take L, which is at most log n times epsilon square, you could find some subspace of dimension L, where the projection of K onto E contains a Euclidean ball of radius R and is contained in a ball of a slightly larger radius, 1 plus epsilon times R. Okay, so this is kind of analogous to the central limit of convexity. I mean, if you project the measure, you get approximately Gaussian. If you project the body itself, you get approximately Euclidean ball. Right? These are the most regular objects in the class. If you want, this is what you get with appropriate projection. That depends on epsilon here, by the way, is due to Gordon. It was an extra log in Millman's form. Okay, so this theorem, one difference is that it gives you a logarithmic dependence on the dimension, which is not as good as what you get in the case of projecting the measure. In fact, there's not much to do because this is indeed sharp. So if you have a simplex with n vertices, after you project it, you again get a point with n vertices, and this will not be close to Euclidean ball unless the dimension is logarithmic in dimension n. So if you project the body, you need to go down up to dimension log n in order to be somewhat close to Euclidean ball. On the other hand, with measure projection, you are nearly Gaussian for higher dimensions, already for dimension n to some constant, to 1/50, say. So this is more well-behaved, as might be expected, because the measure is more kind of average than maybe the support of it, which is the geometric projection. Okay, so I said that we discuss mostly convexity, but let me just say a few words about non-convex distribution high dimension, because many things, I don't know, in machine learning are not completely log concave. But what can you say? Is there anything non-trivial to say about marginals of arbitrary probability measures in Rn? This sounds almost hopeless. What can you say about just some probability distribution in Rn without any assumptions? And there are many cases where you don't have a single Gaussian marginal. Say if you have this Cauchy distribution, random variables independent with Cauchy distribution, 1 over pi over 1 plus t squared, then all of the marginals are again Cauchy with this very heavy tail, very far from Gaussian. However, if you look on many random vectors in high dimension, you see that you can get heavier tails than the Gaussian, but you never get something with a lighter tail. And what do I mean by that? if you take your what do you mean by if you take the what do you mean by, so what you get is usually kind of Supergaussian distribution, the heavier variance in Gaussian. What do I mean by Supergaussian distribution? So let's normalize the density so that its standard deviation is 1 or variance is 1. And if you don't have second moments, let's assume that half of the mass is between -1 and 1. Then if you ask what's the probability of the random vector to be at least t, it's not Gaussian, but it's above what you get for the Gaussian. This is what seems to be the properties that you observe. Okay, so let me make a formal definition. A random variable real valued y is Supergaussian of length L with some parameters alpha and beta if the following holds. So once after you normalize, you divide y by sigma. I think of sigma as being the standard deviation of y, but let's put the median of the absolute value of y, just because maybe you don't have a second moment. So after I normalize y by sigma, what I require is that it has large tail, it's a heavy tail. The probability to be larger than t is bound from below. You have this one-sided inequality, is at least e to minus t squared with these parameters alpha and beta. There will be just universal constant later. So don't bother about them, and also the symmetric condition from the left. So the probability to be small equals than minus t is also at least e to minus t squared. That's strange definition. Let's show an example. If x is uniform in a centered Euclidean body in Rn. In this case, you can compute the density of the marginal by using the Pythagoras theorem. And the density of the marginal is exactly this expression. And you could see that this is Supergaussian of length root of n, and no more. So this density is roughly Gaussian for 1, 2, 3 standard deviations. And then after root of n standard deviation, the density is equals to 0. It is just supported in root of n standard deviation above its median, right? I think I told you that the sphere so most of the mass is roughly in radius 1 over root in a neighborhood of 1 over root of n of the equator. So it means that after root of n standard deviation, you're just 0. Okay, but still you're Supergaussian for root of n standard deviation, sort of length root of n. That's an example. And now comes a theorem which tells you that really with nothing, with no assumptions, you still get something. So some one-sided conclusion. So there are no distributions whose tail is e to minus t quarter in all directions. And apparently there are always Supergaussian directions of length at least root of n. Okay, so here's the following result without any convexity assumptions. So we have some x random vector in Rn. And the only assumption on x that make it n-dimensional is that we assume that x is a density. That's it. Then, under this almost no assumption at all, we can assert that there exists a certain direction theta, such that x times theta, this random vector x times theta, is Supergaussian of length root of n. And there are some universal constants, some numerical constants, independent of anything that I need to put around this form. Okay, so this is something to say about high-dimensional distribution. I don't know what else could be said in such generality. It's optimal up to constant, as we show by the Euclidean ball. And of course, without density, you cannot say anything. You could have just a delta measure or something which is supported in such of 5-dimensional space, so it's not really n-dimensional. You don't see square root of n. But you can relax this density assumption. You could have some condition that works for distributions that are discrete, for example. And I should also say that when x is in under convexity assumption, this was proven by Pirovarov and Paris earlier, and also I had some result earlier that gave it with weaker dependence. There's some log n to the power quarter. Okay, so this was about non-convex situations, and now let's go back to convexity assumption, which is our main topic in these lectures. So we said that if you have isotropic local distribution in Rn, the main effect is this thin shell bound. You know that most of the mass is close is located in thin spherical shell. You have this estimate for the variance of the Euclidean norm of x over root of n. It decays like a constant over n to the alpha. And this exponent alpha is quite interesting. It tells you about the width of the thin spherical shell that captures most of the mass. And it also tells you many things about the quality of the Gaussian approximation. And it was studied quite a lot in the last 14, 15 years. And the estimates improved linearly, kind of. I mean, the first proofs gave something like 1/5, and then Bruno Ferry improved that to clean one quarter, and Olivier Guédon and Emmanuel Milman in 2011 got 1/3. And these three proofs used these concentration of measure ideas. But then something happened, and in 2016, Lien and Vempala improved, first of all, the exponent 1/2, but they also used a different technique. They used a technique called the Erdös Prize equalization, which I'll discuss in my lecture on Tuesday, which can replace concentration of measure and actually brings much better results. And now, just this year, in 2021, Yuan Zi Chen, who gives also 2 lectures in this lecture series, he made a breakthrough and he got a nearly optimal bound. So he got a thin shell of a constant over n, I mean, almost, so 1 minus little of 1. This is now the exponent. And this is really a breakthrough. And it again uses this new technique, this Erdös equalization, in place of the concentration of measure. And I should say that the use of concentration of measure phenomena for proving this central limit theorem for convex sets was hinted by the earlier large deviation principle of Paris, which was earlier. Okay, so let me tell you about the application of this breakthrough by Chen. So first of all, we have very good estimates on the quality of the Gaussian approximation. If you plug in Chen's estimate into the bounds of Bobkov-Chistякov and gets it, you get that if you the following theorem. So if you have a isotropic Markov distribution in Rn, most marginals are close to the standard Gaussian Kolmogorov distance up to an L, which is a constant over n to 1 minus O of 1. This is very, very good approximation. You can kind of say that convexity is as good as independence, because this is also what you get for dependent random variables, constant over n, for typical direction. Okay, for if you're used to Bayesian, you get 1 over root of n. This is for direction 1, 1, 1, 1. But for typical direction, you get 1 over n for dependent random variables. This also another important application of Chen's bound is an improvement in probably the most innocent looking problem in high dimensional convex geometry, which is Bourgain's slicing problem. So this is an important problem. Looks completely simple, but still it is open today, and it was the focus of, it was one of the main problems that drive all progress in this direction in the past 30 years or so. This is the following simple question. You're given a convex body K of volume 1. And you ask, does there exist at least one hyperplane H such that the volume of the intersection of K with H is at least a universal constant, at least 1 over 1,000? And I told you so many things that I told you that the ratio at most square root of 6, told you so many things that you could imagine this should be much simpler than what you already proved. But no, this is still open. What we know is that we may replace this constant C with 1 over Ln. And Ln goes with the dimension. So Bourgain's estimate was n to the quarter times log n. I remove this log n. And now, thanks to Chen, we know that it's n to power epsilon. We can make the power of n as arbitrarily close to 1. Okay, so what's this new idea? What's this new technique that replaces this concentration of measure phenomena that I discussed in such a great detail? So the approach, first of all, is to generalize, to try to prove something stronger, not to prove just a differential bound, but to switch to the Poincare inequality. So this is this new approach. It was emphasized by Bo and Guyen in relation to the Bourgain slicing problem. So what we want to prove the differential bound, we want to prove that for isotropic distribution in Rn, this specific function has very small variance. This is the differential bound. But instead of proving just this fact, we try to prove something much, much stronger. We try to prove that for any function phi with average 0, we have this inequality which is written here. Something much, much stronger, even though all we need is the function phi, which is x over n minus 1. And this is a Poincare type inequality. And let me tell you right away that what Eldon proved in his PhD thesis is that actually switching from this specific function x over n to this much more general formulation is not a terrible mistake, because this function, the quadratic function, is essentially the hardest of all functions. So if you could prove that this function is small variance with respect to the L2 norm of its gradient, then you get up to log factors the same for all functions. Okay, so this is roughly the direction that we're going to, and I want to maybe the last few minutes will be some kind of an introduction to my lecture on Tuesday, and to the Poincare inequality. So the Poincare inequality, I guess that many of you are familiar, or if you're familiar with it, this is an inequality that was actually proven by Poincare, to our surprise, in two papers from 1890 in the American Journal of Mathematics and 1894 in the Palermo Journal of Mathematics. It is about convex sets in dimensions 2 and 3. So in dimension 3, it says the following. If you have any function on the convex set K in R3, which is C1 smooth, whose average is 0, then you can bound the L2 norm of F by the L2 norm of the gradient of F. Okay, so, and if the gradient of F is small, the function F does not fluctuate too much. So you would expect, since its average is 0, to expect its values not to be too large, right? It cannot deviate so much from its average. And there is this Poincare constant here, lambda K, and Poincare proved that this coefficient here is at least, well, 16/9 over the square of the diameter of K. Okay, so this is what Poincare proved. The constant is not optimal, and the sharp constant is actually pi squared in all dimensions. This was proven by Payne-Weinberger many years later. The Poincare inequality is related to Wirtinger's inequality on periodic function in one dimension that was proven 1 decade later. And we are interested in the Poincare constant. The Poincare constant is the best constant you can put in the Poincare inequality. This lambda K, the maximum possible lambda K you could put here in this inequality here. Okay, so at least in the convex case, we know that this Poincare constant, this, we'll explain in a second, this is the eigenvalue of the Neumann Laplacian. We know that it is at least 1 over the square of the constant over the square of the diameter of K. What was the idea of Poincare's proof? Very roughly, I can say it in 1 minute, yes. So we have to use convexity in some way. So you're given 2 points X and Y in your domain K. You can connect them by a segment. And you could use the fundamental theorem of calculus and say that f of x minus f of y is the integral of the derivative of f along this segment. Okay, so f of x minus f of y is, well, smaller than the integral of the norm of the gradient of f along this segment. And now you average over all pairs of points x and y and apply various Cauchy-Schwarzes, etc. And you get a good estimate for this quantity, which is twice the variance of f. So this is roughly the proof by Poincare. It leads to constant that depends very bad on dimension, exponential depends on dimension, but at least it proves the Poincare inequality. Okay, there are many reasons to study this Poincare inequality, and one of them comes from the heat equation. If you consider your convex body and you imagine it as a conducting body whose boundaries is insulating, so heat is not escaping or entering K. And let's write ut of x for the temperature at the point x at time t. Then we have the heat equation, the Poincare inequality, the Poincare constant, is exactly the first minus of the first non-zero eigenvalue of the Laplacian with Neumann boundary condition. The first eigenvalue is just 0 with the constant eigenfunction, and this is exactly the spectral gap, the Poincare constant. And therefore, it governs the rate of convergence to equilibrium. So if you let the heat equation evolve, if you have this initial distribution of temperature and let time evolves, then the hot regions and the cold regions are getting mixed. And at the end, if you wait enough time, you're going to get kind of uniform distribution of your domain because it is not escaping or entering. And you know that the total integral of the temperature is constant, is fixed. And now, by the spectral theorem, the spectral graph gives you the rate of this convergence. And you know that if the initial temperature had average of 1, then also in time t, the temperature would have average 1. And the L2 distance between of ut to the constant function decays exponentially with time. And 1 over lambda k is the relaxation time. Each you need to weight 1 over lambda, 1 over Poincare constant to get a factor 2, let's say, and so on and so forth. So that's the Poincare constant gives you the conductance, the heat conductance of your domain. And in fact, not only that, it also gives you other things, because there are also other ways to measure connectivity or conductance of a convex domain. And one of the things with which I started my lecture, this will be my last slide, I think, is the isopermeability inequality. So let's discuss the isopermeability inequality. You can also define it, at least in a convex domain. So you have this isopermeability constant in a convex domain, and this is the following quantity. You take all possible ways to partition your set into 2 parts, and you look at the measure of the interface, the boundary of A, only the part inside K where K is open, okay, only this blue part here. And you want to minimize the interface divided by the minimum of the size of A and the size of its complement. Okay, so this is called the isopermeability constant of a convex set. And by the way, Sternberg and Zubow in 1999 proved that the info is that it's enough to look at partitions which are half and half. So it's enough to look at sets A whose measure is 1/2. Okay, this is enough. The info is attained for balanced partitions. I think it's not, yeah. If K is centric, yeah, this is true. If K is convex, still convex is not bounded, the form is attained, and this is indeed correct. So we have this isopermeability constant, it also measures the connectivity of a convex set. So what is the relation between this isopermeability constant and the Poincare constant? Well, fortunately, one determines the other up to some factor of 4 or 9 or so on. And this is because of the Chigger inequality and the Bose-Ledoux inequality. The Chigger inequality is true without any relation to convexity. It tells you that the Poincare constant is at least h squared over 4. And in the convex world, you can reverse this inequality and say that lambda is also at most 9 times the isopermeability constant. Okay, so the Poincare constant also sort of determined the isopermeability constant. It also it is also used in other places. It tells you the mixing time of certain Markov chains, and this leads to some algorithms for estimating versions of convex bodies. So it is a rather important parameter in the theory of convex bodies, and we'll discuss it more on Tuesday. So I think my time is up. There were no questions. But okay, so thank you very much for your attention so far.
Thank you very much for a wonderful talk. We need some explanations about the pictures. This one and one on the
this is the beach in Tel Aviv.
And the slide number. Yeah, but the slide number 2, you have a generic mathematician, or is a mathematician?
Minkowski. Wow.
Oh.
How could I? Oh my. Yeah. Let me give Minkowski the honor he deserves. So this is the young, I would say, Hermann Minkowski, one of the founding fathers of the modern theory of convexity. So we mentioned it in.
Yeah, very, very nice. Let's take some questions. I have a couple, but maybe other people would like to go first.
Can I ask?
Yes, definitely.
There were lots of results which said that there were lots of good directions in some theorems. So if you project on good directions, or hyperplanes are orthogonal to them, then something nice happens. But so presumably the set of bad directions is not universal, right? So the set of good directions is universal. But
it's large. It's not universal. It's not the same set for different situations, but it's large.
But can you, is the set of bad directions somewhat interesting? I don't know. Can you reconstruct the measure somehow? Can you tell something about the measure if you know the set of bad directions or something like this? I have no idea. It's just.
Okay, so first of all, you could reconstruct by the Fourier inversion formula. If you know all marginals, you can reconstruct the measure by the Radon transform. I cannot tell you that many things, but I can tell you something. So it tells you one thing. So let's make a tiny bit of symmetries. Let's suppose that our distribution is symmetric with respect to the coordinate reflections. So just these n coordinates are okay. Okay, we have these n 2 to the n symmetries, just switching the signs of the coordinates. Suppose you have this symmetry. Okay.
Okay.
So in this case, I can tell you more. So in this case, I can tell you what are the good and bad directions. I can tell you the direction 1, 1, 1, 1, 1. This one is good, right? I mean, if you have these symmetries like the cube, like the cross polytope, then the direction which is 1, 1 is very good. And in fact, I can describe this. I can at least describe universal set, as you said, a universal set of good directions. So if you know that all coordinates are no coordinate is dominant with respect to the other coordinate, then this vector function will be small. And actually, you have completely good estimate in the CLT, even better than the new developments. You know, you don't have this little of one, and you have lots of information. So so what you could say is that if you see some bidirectional with this pattern of kind of symmetries of coordinate reflection, you could detect the coordinate system to respect to which you have these symmetries. I don't know, it is an answer to an aspect of your question. I'm not sure if this is what you wanted.
Okay, so could you repeat again the set of bad directions on that example would be what? The
set of okay, in that conditional case, the set of bad direction is contained in the set of points on the sphere, okay, that have one coordinate which is dominant, which is one coordinate that is roughly comparable to the sum of squares of all the rest.
Okay, okay. Mm-hmm.
These are the bad directions.
So these are more or less coordinate hyperplanes in some sense,
yeah,
right?
Exactly. Yeah, exactly. Yeah.
Okay.
Perturbation of coordinate, exactly. Yeah.
Yes.
Okay. Any other questions?
I have sort of a naive question. So you've mentioned this connection to the Neumann problem, and indeed, the first non-zero eigenvalue is an important object for this kind of questions. So I'm curious if higher eigenvalues ever appear in sort of in the questions arising from convexity problems.
Yeah. Sure. So the first eigenvalue is equivalent to the asymptomatic problem you divide into two sets. And if you divide into more sets, then there is some relation to higher eigenvalues. There also, I mean, I see you're more, you know, at least as much as I know about this. There also result telling you that under convexity assumption, the case eigenvalue is at most k times the first eigenvalue. So if you have the interval, the frequencies are just arithmetic progression, and so in any convex body in any dimensions, they are more condensed. The case eigenvalue is at most k times the first. Everything's up to constant. So in your work, I mean, the constant is important, and somehow in high dimension it's too difficult the way it is, and we don't put that attention about the precise value of the constant. So that it goes linearly up to some factor of 5, let's say. This is also known. And this division into more than two convex is what the problem of dividing into more than two sets, 3 or 4 more sets. Yes, these are two connections of higher eigenvalues.
Thank you.
Okay, any other question? Then let me ask a very naive one as well. If,
yes.
Do you have, so there were lots of estimates of alpha in the case of isotropic X, but how about the non-isotropic X? Are there also some interesting?
So So you could compare. So okay, so I assume isotopicity just because it's easy, but if you don't assume isotopicity, then typically the Hilbert-Schmidt term of the covariance matrix enters the estimate. Okay, so you could get good estimate, but you have to complement the various the various estimates for alpha, say here, with you should add the Hilbert-Schmidt term of the covariance matrix in an appropriate power.
But so for now, is there an estimate that exists like about the value of alpha? What is the value?
Again, sorry.
So for now, if you don't assume isotropicity, what is the value of alpha? That's not.
So if you don't assume, okay. So if you add here on the right hand side the Hilbert-Schmidt covariance matrix, you get the same estimate.
Oh, okay? I see. Oh, I understand now. Yes.
Okay. If you don't put here anything, then I mean you have the alpha is 0. So you could have if you have anything, you can be just basically uniform smooth in a segment in 9 dimensions, and there's no thin shell or anything, right?
Yeah. And maybe a very, very quick last question. If you look at the Poincaré constant,
the time, not me.
Sorry for the others. I think if you look at the Poincaré constant that in dimension 3, is there some attempt to describe it for bodies in special position?
Yes. So So okay, Poincare constant. So the Neumann one. So yes. So what Chen proved is that all of the estimates I told you for the essential parameter are actually correct for the inverse Poincare constant. So in the isotropic position.
Okay. Yes.
In isotropic position, you have very good estimate for the Poincare constant and also for the isotropic inequality. So maybe I was too quick kind of in the last few slides, but yes. So the point of view is that so many years the focus was on proving this bound in essential.
Right.
Then since Eldan and later Villiers and Pala and now Chen, it turned out that it's much better to prove something much more general, and you have the same conclusion. And for all functions, as you would expect for one specific function in a isotropic position. Yeah. It's
it's amazing.
Yeah.
Well, thank you very much. Are there any other questions?
Thank you.
I don't know, maybe again, fairly naive question.
Please, this is the best question.
Suppose you have a set which is not convex, but which has like several convex pieces glued together. I don't know, 2 or 3 or something. Is it?
What do you think about like a complex, simplicial complex?
Or, no, I don't know. I mean, maybe a sphere with a cap.
Sphere with a cap. Okay, I can do that. Okay, okay.
Or
a yarmulke, like okay.
Yeah, something like. I mean. And so suppose you I don't know, you have a surface measure on that guy or
okay, so let me tell you what you cannot do. Okay, one thing you cannot do is to take 2 concentric spheres. So if you have one sphere of radius r1 and then you have r, why r1? Just r. And then you take another sphere of radius 2r. Okay. And you take something that looks like, say, uniform measure on 1 times 1/2 plus uniform measure on the other times 1. If you take the union of these, it's not convex. It's sphere and ball are the same for us. Okay, let's check the boundary. It's not a big deal to pass the boundary. So if you take the uniform measure on this sphere and that sphere give mass 1 to each of them, then this is of 2 scales, and this persists in the marginals. The marginals are not Gaussian at all. All of the marginals will be again a Gaussian mixture of 2 scales, and you will not get a Gaussian. You just see that they have a Gaussian of variance 1 plus a Gaussian of variance 4, and it will be kind of a double, say like this, and then here will be some like this, just the superposition of these 2 distribution, which is far from Gaussian. So if you component of convex, if you just take 2 or 3 convex sets, then you need to make sure that they have the same normalization. So they cannot have, if each of them has its own covariance matrix, or inertial matrix, then if you combine them, you'll get mixture of Gaussians, which is far from being Gaussian. So if you combine, that's the main thing you need to make sure that you combine pieces with the same kind of spatial normalization. Okay. Another option is to combine many tiny, not just 2 or 3, but many tiny pieces. Okay, this makes sense to different directions. So if you have many tiny pieces, none of them is dominant. In this case, yes, you could expect something to, but this is a completely, let's say, each concrete problem looks like a completely different story. So I don't know of anything general to say about situations where you have many small components. There are many types of interactions.
Okay, yeah, no, so I guess maybe you can, like, if you have, I don't know, if you have a reducible Markov chain or dynamical system,
okay.
you decompose it into pieces, and then the whole thing is going to be built up out of those pieces. So maybe if you have convex pieces, something similar. Like you were saying for superposition. So in this case, you have a sum of 2 things. Each thing is kind of.
Okay, but sum is a bit too easy because sum of concave is again non-concave. So if you take the sum of convex pieces independent, then it's another case of non-concave. You don't want to maybe take some nonlinear operation to make it an interesting problem.
Okay. Anyway, so
it's a good. I mean, I don't have anything intelligent to say. It's an interesting direction to think about.
Yeah. Okay. Sorry.
No, good.
Okay. So let's thank the speaker again, and let's look forward to Tuesday when we can ask more questions, follow the second talk. Thank you very much.
Thank you.